Other problem. Here's a set of coordinate axes. And about halfway between here and here, and halfway between here and here, maybe a little lower than that, at about a 45-degree angle, along the line at a 45-degree angle here, I'm going to put the point 1, 1, so that 1 is here and 1 is here. Now, I want you to start with a graph like this, and I want you to sketch the graphs of y equals x to the p, for the y factor, y factors, 1/2, 3/2, 2, 5/2, and 7/2. They've already constructed the graphs for 3/2 and 2 in preceding problems, but we want to add the graph for 1/2, the graph for 2, the graph. This should be 7/2. I wrote 7/7 because I wasn't paying attention. Okay, so we're going to sketch these graphs, and then estimate the curves, and by estimate I mean sketch the curves as you would estimate their position. For y factors, three, and 4. Don't actually construct them for factors 3 and 4. Just estimate where they are based on where these curves are. Then, for the factor 3 curve, estimate your y values for x equals 1/4, 1/2, and 2. Then, on another graph, because this was going to get kind of cluttered, carefully construct the factor 3 curve, and estimate I'll write it this way: f of 1/4, f of 1/2, and f of 2. And then compare your estimates here with your estimates here. Your results should be reasonably close together, but we can't expect them to be exactly the same because, of course, this curve was an estimated curve. This curve is more carefully constructed. But see how well you estimated the position of this curve based on this construction. At this stage, you might or might not have proven it, but the factor 3 curve represents the function y equals f of x equals x raised to the power of log 3 divided by log 2. That is, this is an x to the p function with p equal to log 3 divided by log 2. Now this is something that bears analysis and proof, but if you haven't proved it, I'm still going to let you use it. And this is the first time I'm going to actually ask you to do some calculations, and you will need to use your calculator because log 3 and log 2 are not numbers that are going to easily be calculated by hand. There's almost no practical way of doing that. Okay, so we have this, and then evaluate f of x for the x values that we used down here, so you can compare how well your constructed curves allowed you to predict the values of this curve. So, so that's for x equals 1/4, 1/2, and 2. And then we want to compare this with previous results. The factor 2 curve has a very specific shape. What is this shape? Now let's leave it at that. What is this shape? And then prove that it is so. The proof is quite simple, and if you see it after having tried to prove it, once you see how it is proved, if you fail to actually prove it, and that always is a possibility because proof is not difficult, it's not that easy. You'll hit yourself upside the head, gently I hope, no concussions, if you find that when you see how it's actually proven and why it's true. Really, to prove that it's so, you just have to think about why it would be so in terms of the construction. And then you just put that into words in some way, and more or less you should have something that's at least equivalent to a proof. What's the difference between the factor 1/2 curve and the others? What is the limiting value of y as x approaches 0 for the factor 1/2 curve? Okay, so we start at any point, keep going halfway, 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 halfway. X will approach 0 as a limit. If we continue doing that, what's going to happen to the y values? we can sort of complete the picture that shows the general behavior of these curves if we sketch the factor 1 curve. And then there's one other curve that we want to talk about, and that is the factor 0 curve. I'll ask, why is the factor 0 curve undefinable, provided we follow the usual method? So we'll say unless zero, 0 is declared to be the starting point. And again, this is a fairly challenging question. Don't worry about it if you can't get it, but hopefully you'll give it some thought. Factor 1 curve is very easily defined, and let's say implicitly that with each of these curves, for right now, we're following the instruction we started with, which is to start with 1, 1. And you could ask yourself, okay, if we start with a point 1, 1 and try to sketch the factor 0 curve, just what is it that we get? And I could throw the further hint in there. Is it a curve? And let me clarify two things. When I asked the limiting value of y as x goes to 0 here, I was talking about for the factor 1/2 function. And also, a straight line is a curve. It's a curve that doesn't curve, but it is still something that we want to call a curve. But there are other things that we simply could not call a curve.